This is a binary stiffness compliant mechanism that can achieve two different states of torsional stiffness by triggering a simple switch. One state is very compliant while the other state is very stiff. The mechanism is a rotational analog to the translational binary stiffness mechanism discussed in part 1 of this mini-series. In other words, this mechanism does the same thing as the mechanism in that video, except that it rotates instead of translates. Thus, much of the same principles that govern how the mechanism of the previous video works explain how the mechanism of this video works. Note that similar to the translational version of the mechanism, this rotational analog also consists of 3 components. 1. A compliant bistable switch, which can be triggered to achieve stability in 2 different resting positions. 2. Angled blade flexures, which are designed to buckle and curve outward when the switch is pressed inward. And 3. Rotary blade flexures, which stiffly constrain the shuttle and thus restrict it from moving in any direction except about the rotational axis, which is defined by the intersection of the 2 rotary blade flexure planes. Really, the only difference between the rotational mechanism of this video and the translational analog from the previous video is that the rotary blade flexures are not parallel and thus do not permit a translation. When the bistable switch is in its initial undeformed configuration, the angled blade flexures are straight, and thus, similar to a truss, stiffly constrain the mechanism's shuttle so that it can't rotate about the axis defined by the rotary blade flexures. But when the bistable switch is pushed inward, those angled blade flexures buckle, and thus lose their constraint capabilities so that the shuttle can freely move with the rotation about the desired axis. Moreover, the now pre-stressed angled blade flexures exhibit negative stiffness in their curved configuration, and this negative stiffness cancels out the positive stiffness exhibited by the rotary blade flexures, which results in a mechanism that achieves a near-zero torsional stiffness. To better understand the concept of negative stiffness and how different stiffness values can cancel each other to achieve near-zero stiffness values, be sure to see part 1 of this mini-series. You'll note that even the measured torque angle plot of the mechanism is similar to the force displacement plot of the mechanism's translational analog. The most noteworthy difference is not with the plot itself, but how the rotational mechanism was loaded. Since cables cannot be loaded in compression, a counterweight was used to assist the instron in loading the mechanism over its full range of rotation. This was done by running 2 cables within grooves on the circular portion of the crescent-shaped shuttle. If you're still confused about how this mechanism works after watching this and part 1 of this mini-series, you can read more about the mechanism in our published journal article. A link to the paper is provided in the description below. Also, be sure to see the other parts of this mini-series about binary stiffness compliant mechanisms to learn more about how they work and their potential applications. Thanks for watching The Facts of Mechanical Design.